Hello and welcome to Disseminate, the Computer Science Research Podcast. I'm your host, Jack Wardby. Today is a special day because for the first time I'm joined by two guests. It gives my great pleasure to welcome Jain and Sarah Wooders to the show, who will be talking about the Skyplane project. Sarah and Paras are both PhD students in the Sky Computing Lab at UC Berkeley. Welcome to the show, folks.
Thanks for having us.
So let's jump straight in then. So maybe you can tell us a little bit more about yourselves and how you both became interested in researching in the data management area.
So I'll start. So I started my PhD about 5 years ago. Here I've gone through several phases. I actually started my PhD in machine learning. So I was working on machine learning systems, infrastructure for scaling up large-scale models. And one of the most pressing problems when scaling up these models is that the data sets become very large and unwieldy. And so just from my research itself, I started to try to look at how could we try to solve these data bottlenecks when training these large models. And so these types of models, you can think of these like diffusion models or GPT, and these type of models, they can ingest like terabytes of data during the training process. And then the models themselves are very large. They can be many gigabytes themselves. And so this was a really firsthand problem that I had encountered, just moving these parameters and data sets around. And so I made this transition to networking and systems research with the Skyplane project about 2 years ago.
I also had a very similar motivation. Prior to coming to Berkeley as a PhD student, I was actually working on a startup, training these e-commerce models to basically classify different types of products based off the product images, basically. And with that project, moving around these huge image data sets that I had was a really big pain. I was often switching between GCP and AWS, depending on what tools I wanted to use. And so then when this whole vision of Sky started coming up when I was in the lab, I was really immediately drawn towards solving specifically the data gravity problem around moving between clouds, since that to me seemed like the biggest challenge.
Awesome, yeah, it's a nice segue actually into the Skyplane project. So maybe you can tell us a little bit more about the project. And I think you hit on the word there, data gravity. Maybe you can tell us a little bit more about what that is and kind of what the problem is you're trying to solve.
Sounds good, yeah. And before I do that, I just want to give a one-sentence intro on what the Sky Computing Lab's goals are. So here at the Sky Computing Lab at UC Berkeley, we are trying to build infrastructure and platforms to enable applications to run seamlessly across multiple cloud providers and cloud regions. And so, again, there's a variety of different reasons for that. I can go into that if we're interested. But the most important problem you're going to encounter in this cross-cloud or cross-region environment is something called data gravity. And so data gravity, I think, is actually very simple. It's that when you work with large data sets in the cloud, it is, number one, slow to move that data between different regions, right? It can take many hours to move large data sets between different regions or clouds. Second, it's very expensive to move that data. And why is it expensive? Well, in the cloud, you have to pay for egress fees. So every single byte of data you move over the internet or a cloud network, you have to pay. And so because you have to pay for that volume of data, it can cost a lot of money. And to ballpark, it can cost anywhere up to 10 cents per gigabyte to move data in the cloud. So to move let's say a 200 gigabyte training data set, that's equivalent to spinning up a 34 node cluster of VMs, M5X large VMs for a whole hour, right? So it's really expensive, actually, these data transfer costs in cloud. And the third factor of data gravity is the complexity of moving this data. So you end up having to use a patchwork of different tools that are mutually incompatible and work with specific cloud sources or cloud destinations. And so this data gravity problem, again, that it's slow, expensive, and complex to move data in the cloud environment means that's kind of the key problem we want to solve in the Skyplane project. And so Skyplane's goal is to make data transfer in the cloud essentially high speed, cheap, and very easy. And I can go into details about how we kind of accomplish that, but at a high level, that is the goal of the project.
Awesome, cool. Yeah, I actually read the the manifesto of the Sky Computing Lab a while back. There's like a paper on archive, right? I remember reading it and been really interested in it. I know it's from I think the thing that kind of piqued my interest in it as well was the sort of the economics of this the idea of of moving data between clouds or whatever, and what that sort of marketplace might look like in 10, 20 years in the future. But anyway, I digress. It was a very interesting read. So yeah, you guys work on some really, really cool problems. So yeah, I guess you mentioned it a little bit there about the existing tools sort of not being efficient. So, I mean, I've stolen this line from your slide deck. So what does life in the sky look like now, today?
I think the reality is there's actually very little life in the sky right now. Like multi-cloud is actually pretty uncommon. You might have some companies doing migrations every once in a while, but the actual vision of sky computing, which is being able to choose the best of breed software from different providers and combine them into a single application, is I think still pretty far off. And a big reason for that, which is what we believe, is that this data gravity issue and these really high egress fees that cloud providers charge are basically preventing this from happening. So yeah, part of our motivation with Skyplane is to be able to sort of achieve that vision by eliminating data gravity.
Yeah, I guess just from if I was AWS, for example, I guess I want to lock in people to my cloud as much as possible, right? So yeah. I guess they have an incentive to make it as difficult as possible for people to move, right? So you keep spending money with them. But I guess Skyplane is going to help alleviate some of these problems and make it better for the end user at the end of the day. So maybe you can tell us a little bit more about the architecture and the design of Skyplane and how you went about making these design decisions to kind of address this gap.
Yeah, it might be helpful first to outline like why the performance for current tools is so bad first. And when we actually profiled cloud networks, what we found was really surprising. So first of all, when you begin to transit between different cloud providers or even two regions within a cloud, it's very common to encounter congestion. And so you'll find this on places such as transatlantic network routes. That's a single kind of fiber cable that's kind of that they had pulled that's shared across many, many thousands of customers. And so that's going to be a highly congested resource. You have to compete for capacity there. The other challenge is that we actually find that cloud providers actually throttle network data transfers. And so this is applied, for example, in AWS. If you get a VM, even if the network could sustain 10 gigabits per second of egress, they're only going to let you transfer data at 5 gigabits per second, right? And so they're actually explicitly throttling your network transfers there. And then on top of that, again, beyond just speed, the costs are still real. And so that can vary anywhere from 1 or 2 cents per gigabyte if you're transferring between two regions in AWS in the same cloud to anywhere up to 10 or even 19 cents per gigabyte for some regions. So the cost structure is also very complex and hard to navigate as an end user. So what Skyplane does is that we have a system that periodically profiles the internet, essentially, between all of these clouds, and it measures the throughput and the cost for moving data. And so we end up getting essentially this map of the public cloud internet, right? And so we have all these different routes between all the providers, and we can see the throughput from different region pairs. And so we go through this kind of cartography exercise, but after doing this, we now have a map where we can kind of begin to navigate and find more efficient or more optimal network routes that can route around congestion in the public cloud's network. And so with these two parts, we first kind of profile the network and then we kind of plan around it. That is really one of the key techniques we leverage to achieve better performance.
That's fantastic. So you've got an upcoming NSTI paper that's going to talk all about this in some depth. So I think that this primarily focuses on how you optimize the transfer, right? So the cost and the throughput. So can you maybe tell us a little bit more about that paper and can you dig into some of the insights and techniques? I think you touched on them a little bit previously, but go into a little bit more depth and how you leverage them within Skyplane.
So I'll talk about this, and the NSTA paper that we wrote is on unicast. So what that means is from a single source to a single destination, how do you move data? So I'll briefly touch on that. I actually would like to also leave some time to discuss some of the upcoming work that we have under review now that's, I think, really exciting too after this unicast. So for this single source, single destination network transfers, again, as I mentioned, we profiled all these cloud networks. We got this map, if you have n regions, we have this n squared grid essentially telling us the performance between any source and any destination. And we have an optimizer that actually carefully plans routes in cloud networks. And so really the hard thing here that we want to solve is the optimization problem is that we want to minimize the cost of a transfer subject to a user's desired replication time constraint. So the user might say, I want to move 100 gigabytes of data and I want to finish in 10 minutes, right? And so subject to that, we need to find a way to move that data at the lowest possible cost. And so we'll use a variety of different optimizations, such as this overlay routing I mentioned, where we route around kind of slow parts of the cloud network. We also have other tricks. So we do things like we automatically manage elastic VM pools and parallelism. And so in cases like where the cloud provider like AWS throttles the user, we can essentially provision more VMs to burst past that. throttling constraint, right? And so our optimizer also kind of in the same integrated problem decides when to deploy that parallelism trick to essentially conquer throttling. And also we perform automatic bandwidth tiering and compression that help reduce egress fees, right? So it turns out it's really surprising, but it's well worth paying the extra money to get some extra vCPUs to run some compression and deduplication so you can reduce your egress fee. And it's almost like a 10-to-1 ROI there, right? You save a lot of money there in aggregate by doing this compression and deduplication, which is really surprising. That's another insight that we leverage.
Fascinating. Is there like a tipping point there after which, like, kind of up to a certain level, it depends how much data you're transferring, whether you actually get a benefit, right? Or is it kind of always a win?
It's really interesting. So we don't necessarily have strong support for very small files. So if you're doing like, 512 kilobyte key value kind of store, you want to do partial replication of that, I mean, it's not necessarily the right tool for the job. So here I would think, if you're moving 5 gigabytes or more, you'll probably see a strong benefit from using Skyplane compared to existing tools. But again, we keep putting more and more optimization in the system. It's open source, and we have a very vibrant community of contributors who are helping us optimize the performance further and further. So I think that tipping point is starting to shift lower and lower, which I think is really exciting.
Yeah, the main reason why, there's sort of like that 5 gigabyte threshold is because Skyplane is actually creating VMs in your AWS account to run that transfer. And so that startup time for the VMs is going to take about 40 seconds, which is sort of a constant overhead that we can't really do much about unless we have like some continually online Skyplane cluster, which we don't have right now. So because of that, it's only really beneficial for larger transfers.
Just to summarize briefly, then, so the kind of the four ingredients in the secret sauce is the overlay routing, being able to dynamically adjust the number of VMs, the network tiering and compression, and then being able to have parallel TCP connections, right? They're the four sort of ingredients that go into making Skyplane. Cool. So you mentioned there about other maybe further optimizations that you might consider as well. What's on the roadmap there for that? Like, what other things do you think could be interesting?
So one recent follow-up paper that we just submitted actually was on how can we extend the optimizations in Skyplane unicast to multicast or broadcast. So this is basically where you want to transfer data from one source to multiple destinations. And in this scenario, you can actually get much more significant wins in both the throughput and cost improvements because you might be over and over again using expensive links. So oftentimes in AWS, you'll have regions that are much more expensive, so maybe 19 cents per gigabyte, as opposed to the standard 1 or 2 cents per gigabyte. So one optimization that we do in the multicast scenario is we can move the data once from an expensive source region to a cheaper overlay region, and then broadcast the data from there. Another really important optimization that we do is we basically have multiple stripes of the data. So as opposed to sending all the data along one distribution tree, we split up the data along multiple distribution trees so that no single node or single path is burdened with all of the data. So from those two optimizations, we actually end up getting very significant cost savings on both the egress and then also throughput improvements.
And this isn't in the NASDI paper. This is like additional work that's under review at the minute at another conference,
yes.
Right?
Yeah.
Mm-hmm. Yeah. Okay, cool. Well, good luck with that submission. Hopefully it gets in. I had while you guys were talking there, I was thinking, and kind of going back to what we said at the very start of the show, of how it's in kind of cloud vendors' interests to lock people in, right? And how they essentially throttle things to make sure to in various scenarios they throttle things, right? So you don't get the full bandwidth or whatever. Is there any sort of kind of, not concern, but if they detect that someone's doing this, kind of throttling other things to kind of stop them moving to different cloud vendors, for example? Like, I'm thinking that if all of a sudden the cloud provider becomes sort of adversarial in this.
I think that would be really hard for the cloud providers to do because we use all public cloud APIs. So they would have somehow figure out that it's Skyplane running this API. And then the other thing is that we also run inside of our users. It's the users' VMs that are actually executing these transfers. So it's not like there's sort of some Skyplane service that they can block. It's all something that you run yourself, and it's open source. And like, just because we're sort of saving costs with the user, I don't think necessarily means that it's bad for the cloud provider. Because if you think about like, why are the clouds actually throttling, or why are they making some paths more expensive than others? It's sort of, in a way, like trying to shape demand, right? So what Skyplane basically allows is for users to actually, in an automated way, react to the pricing that the cloud providers set. So I don't think it's necessarily a bad thing for the cloud providers.
Cool. So I guess I'd like to touch on a little bit about the implementation of Skyplane. Can you maybe describe a little more about how it's implemented, how long it took you to implement, and what the implementation effort it was like?
Yeah, so it's open source, and so that's a really, I think, important part of the project is like we wanted to ship this to the real world. We wanted to see this actually be implemented to real applications because, you know, it's going to improve our research long term to learn about the use cases for which people are using Sky computing, right? So we had an initial implementation actually done for our first paper submission within about 3 months, actually. It was a very, very quick project kind of turnaround that way. We had built the system originally in a few different languages. So I had done some initial tests with like Go or C++, and then we figured out it's all IO bounded. So actually, however remarkable that is, the majority of the prototype is written in Python. And so we're able to get, you know, hundreds of gigabits per second of aggregate throughput with this, right? Though, again, just very careful implementation using careful system call interfaces like splice and kind of zero copy kind of mechanisms. But yeah, I mean, that was sufficient to get very high performance. That has really kind of enabled high velocity and means our community of contributors are able to kind of upstream new cloud connections, new object store interfaces, or even kind of new kind of technologies like different encryption techniques very quickly, right? And so the on-ramp to kind of contributing back to the project is very low. And so, you know, I think that's been a really important kind of enabler for the project today.
Sure, I guess having it in a language like Python makes it a lot more open to a lot more people, right? So as a user, then how do I interact with Skyplane? And so what's my experience like? As if I wake up tomorrow and want to move some data around using Skyplane, how does that look like?
You can just pip install it. It's very easy. So you use this pip install Skyplane, and now you'll have the Skyplane CLI. And so if you wanted to do a transfer from, let's say, between two AWS regions, all we'll require you to have is the AWS CLI installed and have your cloud credentials logged in. So, you know, I guess you'll do like AWS configure auth or something. And, you know, as long as that's kind of set up, which if you're using AWS, you probably already have, Skyplane will just work. And so behind the scenes, you know, Skyplane supports scale to 0. So when you kind of just installed it, there's no VMs, there's no state, there's nothing running. Everything lives on your local laptop. But as soon as you type Skyplane CP, and you might say S3 in the source and S3 in the destination, then Skyplane will actually provision virtual machines to actually serve as ephemeral cloud routers. And that only exists for the duration of your transfer. It's actually a big advantage to what using Skyplane from the user's perspective as compared to other systems which leave VMs running all day, kind of cost a lot of money. This is actually really, we started out trying to design this for other researchers like us. So, you know, small scale users who have a lot of data though, right? And so the system kind of is there when you need it and scales to 0 and deprovisions everything and cleans it up when you're not, right? And so behind the scenes, there's a lot of complexity in terms of provisioning, doing things securely, so managing encryption and cloud keys and IAM and all this stuff. But that's all kind of abstracted away behind the CLI. From the user's perspective, you pip install and you're ready to go.
One thing I'll also mention is we also just recently released a Python API. So now you can actually directly from code provision a Skyplane basically cluster and then execute transfers on top of that and deprovision everything from Python. So we built this actually because we were hoping that people could sort of build applications on top of Skyplane. So we actually have an example of like ML data loader and also an Airflow operator that are built with Skyplane's API on our documentation page.
The deprovisioning thing would have saved me a lot of trouble over the years because I've numerous people I know of leaving VMs running when I shouldn't have done and stuff, right? Because that's cost the university a lot of money, but I got shouted at for it, right? So anyway, cool. Yeah, so you said some apps were built on top of Skyplane. So can you maybe tell us a little bit more about those? I'm not familiar with Airflow.
So Airflow is the Swiss Army knife of essentially data pipelines in industry. So for a lot of ETL workflows, Airflow is an orchestrator. So you know it's a service where you can schedule workflows, meaning like here's some job inputs and here's a particular computation you might run, like running a Spark SQL query, and then you want to write the outputs to a particular destination, and you might say I want to run that job every night. So it's essentially this system to kind of orchestrator that runs these workflows over data pipelines. What's really common is people have data in 1,001 sources. You might have data in AWS S3, then Google Cloud Storage, then Snowflake. Then you might have even data in, software as a service providers like Salesforce or, Facebook marketing. And then you might even have data on-prem, and then it gets very complex. And so in Airflow today, the state of the art is there's these kind of S3 to GCS, S3 to Azure Blob, S3 to Azure ADLS kind of connectors. And each one has a slightly different interface, right? And so it's a lot of user burden to learn how to use this tooling in order to get your Airflow jobs to kind of operate and consume data from all your data sources. But this is, again, very important for organizations. We have an integration with Skyplane and Airflow that enables users to effectively bridge data from any source and any destination that's supported in Skyplane, and we will take care of moving that data at really high performance. So, if you actually use this, even if you use, like, let's say the baseline, S3 to S3 connector for Airflow, you might only get data transfer speeds of 20 megabytes per second. But with Skyplane, we're able to complete those transfers at, tens of gigabits per second. So you get better performance, lower cost, and it's easier to use, quite honestly, because it's a single tool that covers all of these cloud destinations.
Great stuff. Yeah, so the Airflow is not part of the same project, right? This is just sort of, it's not within the Sky Computing Lab. It's a totally separate.
It's about 100 lines of code, actually, in our examples. It's very simple to use over our API. So we expose all these parameters up to users, and you can programmatically kind of configure, we call it a data plane. That's like this group of VMs that runs across the clouds, and kind of describe what inputs and outputs you're kind of plumbing through the system. So, it's actually very easy to use, and our intent is like to have this be upstreamed into kind of other open source libraries. I think Sarah also mentioned we have another example of a cross-cloud ML data loader. So if you have data in one region and you want to train on a GPU in another region, we have an example where you actually will use Skyplane's overlay to plumb the data from the source to your GPU, right? And just stream it directly from object storage to the GPU. And so that's another kind of simple example that's actually implemented very cleanly and very simply over our API.
Cool. We've thrown up kind of some numbers around across the course of the chat so far. So I'm guessing you've done some sort of evaluation of Skyplane and under various different experiments. So I was wondering if you could maybe talk a little bit more about some of the experiments you've run. I guess maybe just revisit the questions you were trying to answer and kind of talk about how those, I guess what you compared it against maybe as well, right? And because that's kind of not obvious because it's a new thing, right? So yeah, maybe tell us a little bit more about your evaluation of Skyplane is where I'm getting at. A long-winded question, I apologize.
So I can talk about the Unicast project. So that is on Archive. You just search, you can find it, or on skyplane.org. We have the paper linked. So we compared against several vendor baselines and some open source / academic baselines, but the vendor baselines are very strong. So what we compared against are AWS Data Sync, GCP Cloud Data Transfer, and then we compared against Azure has an AZ copy service that allows for high-speed data transfer between Azure services. And so these are cloud provider specific services, so they should be highly optimized and overfit in some sense to each cloud provider. And they have visibility into their own networks and capacity and stuff. So these tools are quite strong baselines in some sense that the cloud providers themselves, this is their sanctioned way of moving data. So relative to some of these tools, for example, like against Azure Data Sync, we're up to 5 times faster for data transfer within a single cloud, right? And so already, even just if you're in AWS and you don't use another cloud provider, you can get up to 5 times higher throughput than AWS Data Sync, and it's substantially cheaper because we don't charge a service fee, right? AWS Data Sync charges you the egress fee plus an additional service fee per gigabyte you move. You get better results, obviously, moving between clouds. The results vary there, but again, the vendor tools often don't have very good support for cross-cloud data transfer, right? They often only allow you to move data into their cloud, but they don't support generally moving data out, for example. So it's a little hard to evaluate. We also considered some academic baselines. So, for example, we considered Grid FTP, and we have better price and performance compared to Grid FTP. I think the most interesting, exciting results are actually in some of the follow-up work.
Yeah, so in the multicast work, we had a couple of baselines. So one of them was AWS S3 multi-bucket replication. So S3 basically allows you to write these replication rules. So like when you write to that bucket, it automatically gets replicated to a bunch of other buckets that are connected to it. So that was one baseline we had. And another one was BitTorrent. So that's a really common tool people use to basically disseminate data from that might be located in one place to a bunch of other destinations. So we did a bunch of experiments basically comparing about 100 gigabyte transfers from one source to about 6 destinations. And our numbers are usually around like 60% cost savings and almost up to 3 times replication time speed up. And I also want to note that the results actually get better and better the more destinations you add. So for larger sets of destinations, the cost saving opportunity and also the replication time reduction opportunity actually gets bigger than that.
We maybe spoke about this a little bit before earlier on, but sort of like, what are the current sort of limitations of Skyplane?
So Skyplane today supports cloud-to-cloud destinations, and we have very limited support for on-prem to cloud, but that is a very hard problem. But we have a student in the group who is working on high-performance on-prem to cloud data transfer. But that is probably one of the biggest areas that our users have been asking for new solutions in, and that's something we're trying to evolve the project to better support.
Sure, cool. You obviously get a lot of feedback, or you have got a lot of feedback from people actually using the Skyplane, which is like, I guess is quite different to most sort of academic projects, right? Most of us kind of, we do something and it disappears into the ether and we're lucky if anyone looks at it again. So my next question I normally ask is kind of how, as a software developer, how can I leverage the findings in your research, so in Skyplane in this case? I guess it's just kind of just kind of go and use it and see how it works for you, right? And feedback in that way. But I guess like what impact do you think your work with Skyplane can kind of have for the average software developer in their day-to-day life?
Yeah, so I think for the average software developer, if you have large amounts of data, so anything more than like 10 gigabytes probably, and if you're having to use that data from a location that's not the same place where that data is, so whether it's a different region in the same cloud provider or a different cloud provider, then Skyplane can help you access that data faster. And also, if there's data that you have to synchronize that's maybe living in different locations, you can also synchronize that data faster using a tool like Skyplane. There's other applications, sort of higher level applications that we've been sort of starting to think about designing. So for example, things like disseminating model weights are also containers to a large number of destinations. So I think especially something like a high performance container registry built on top of Skyplane multicast could be something that's really useful for sort of higher level applications used by software developers as well.
I mean, I guess kind of working on this project, you seem to have covered some really fascinating areas and problems. But are there any ones that sort of stand out as being the most interesting, or maybe like unexpected lessons that you've learned like while working on this project?
I think for the multicast work, I was always really surprised by how crazy some of the distribution trees ended up looking. Like we had some examples that were like a multi-cloud transfer from AWS to maybe some other AWS, GCP, and Azure regions. And there were some really unintuitive paths, like going from AWS to GCP, back to AWS, and then to Azure, that were part of the tree that were really surprising to me, but I couldn't, and they almost seemed wrong at first, but I couldn't figure out a better solution. So I think they're probably right. So that was really surprising to me. Like, I think it's sort of the erraticness of cloud pricing causes the optimal distribution tree structure to look really, really strange in some cases.
Do you notice it changed quite significantly between sort of like day to day as well? I mean, I'm not really too familiar with how dynamic cloud pricing is, but did you notice like doing the same job on a Tuesday one week to then doing it on the Thursday could result in a completely different distribution tree?
So cloud pricing itself is actually very, very static. I think it might, like, people might change their pricing around like every couple of years. I think something that's more likely to change the pricing models is the impact of incumbent clouds. So there's some new cloud providers who are basically trying to compete with the big players by offering free egress. So Cloudflare is one of these. And we actually found another sort of surprising result that we had was that you can actually use these clouds like Cloudflare as kind of intermediary points. So if you're transferring from AWS to GCP and Azure, instead of paying egress twice, so once to Azure and once to GCP, you can actually transmit the data through Cloudflare, pay egress once, and then broadcast the data from Cloudflare to the other clouds. So I think that's potentially something that's more likely to impact pricing in the long run than like sort of dramatic changes to cloud provider pricing.
That's interesting. How easy is it to add support for like a new, so let's say some startup happens tomorrow about a new cloud provider. How easy is it to add support for that for Skyplane? Is it a lot of work or is it pretty simple?
So if they're S3 compatible, it's not that hard because worst case, we can just use VMs in other clouds to basically just connect to their S3 compatible API. I guess, do you want to add to that?
Yeah, so we've been collaborating pretty closely with some contributors from IBM who have been working to add IBM cloud support. I think their PR is like under 800 lines of code. So, it is some work today, but it's not like tremendous. I think it's something that's pretty doable, and we're working very hard to kind of reduce the amount of changes necessary. In fact, one of the critical projects that are kind of starting around this effort is to create a Sky Kit, in some sense, common provisioning infrastructure that we can share with Skyplane, but also with other projects. With this idea of modularity, kind of leveraging existing cloud provider integrations with tools like Terraform, for example, so that you don't have to keep reinventing the wheel and rewriting integrations to clouds. It should be really easy and really simple to add these new cloud providers.
Great stuff. So yeah, I guess the next question is something I often ask my guests as well, is that obviously from the initial idea for a piece of research, piece of work, to where we are now, were there things along the way that you tried that failed and the listener might benefit from knowing about cyber? They don't make the same mistake again, or it's just an interesting dead end that you found?
Yeah, so since starting the project, I actually didn't want to work on this problem necessarily. I wanted to kind of work at higher level applications. So, how can we kind of build these applications in Sky computing contexts, such as machine learning? But, as I started digging into that problem, I was like, the most basic infrastructure here is abysmally slow and expensive, right? And so that has focused our research around it. And it's kind of like in the beginning, I was a little hesitant to work on this problem, but it actually turns out just in a simple data transfer setting, there is so much work that can be done. And so, the insight here, I think I took away from this experience is kind of start simple. I really wanted to build some big overarching system to let you do kind of cross cloud machine learning or data analytics or something. But really, it's even just the really simple problems like data transfer that really are most critical, right? I never really appreciated the complexity of how to kind of accomplish this in a cloud environment easily. I think one really important thing also that kind of enabled the research was kind of having this open source mindset. So, academically, I think there was a little skepticism initially. What would the insight be? What would the key kind of optimization space look like? Taking an open source kind of mindset, kind of looking at the best of breed tools today for data transfer and just profiling them carefully. That's where we kind of discovered this overlay technique, and then kind of the research agenda kind of fell into place from there, right? And so really it's just taking the best of breed tools and kind of hacking on them and trying to figure out incrementally, how can I just make this better or better and better?
Yeah, that's really nice. When did this idea initially start? How far back are we talking? Is it like been a multi-year sort of project or more recent?
Then to went about 2 years since I started thinking about this area. But as I said, the first implementation, very incremental, very quick. We got it done in 3 months or so for that kind of first paper submission. But since then, it's a large team here. We have about 5 PhD students working on the project and several undergraduate students on the project too. So it's been very encouraging to kind of see how the project has grown over time.
Yeah, I guess what's next for Skyplane then? Kind of maybe the short-term vision and then the long-term vision and some of the stuff that you got in the pipeline.
So I feel like at this point, we basically have these really powerful communication primitives, like whether it's unicast or multicast, the ability to move data really quickly and cheaply across clouds. So I think that what the main things that we've been thinking about right now have basically been what are sort of applications that we can now build on top of this. So one thing that we've been thinking about is potentially building a Sky storage layer. So basically sort of like a shared object store that spans clouds, except the underlying replication is done by Skyplane. So if you write to one location, that gets replicated by Skyplane really quickly and cheaply to all the other places that you might want your data accessed. And so we can kind of co-optimize that with object placement to basically have like a very fast, cheap replicated object store. Another thing that we've been thinking about that I mentioned previously is also building either a container or model registry. So this was kind of a use case we stumbled into when we were looking for baselines for the the multicast work. where we were finding a lot of other similar systems were actually focused on building container registries. So if you have a new container, how do you push that to a bunch of destination locations where you might want to run that container? So one other thing that we've been thinking about is like, could we basically build like a container publishing, or also similarly with models, like model weight publishing platform on top of Skyplane multicast?
Some really interesting directions there and work that's going on. This would be a nice time maybe to talk a little bit about some of your other research. I know there was a paper at CIDR recently about lake houses. So maybe you could give us the quick elevator pitch for that and tell us about some of that work and how that links to the Skyplane project.
Yeah, so I was working on the Skyplane project, and you look at what do people store in their buckets. Well, it's really surprising, but a ton of it's just Parquet. And so people are storing tons and tons of this relational data in their data lakes, in effect. And so one of the things I wanted to understand was, what are the current storage formats for this tabular data and these data lakes? And a very, very recent trend in the industry has been the development of the lakehouse architecture. So here you have disaggregated compute from storage. And usually this means you're going to store this data in object storage, so like AWS S3, for example. And then you utilize a technology such as Delta Lake or Apache Hudi or Apache Iceberg to provide ACID on top of that, right? So now you have transactions. This is an emerging paradigm in this kind of a analytics area, but it's very appealing because now you're storing your data in Parquet format, which is highly compressible, and it's in a data lake, right? So you can scale to 0 when you don't need to do any queries. And it's very cheap to store data in Amazon S3. And so the Lakehouse benchmark, which is what the paper we submitted to CIDR was, or LH Bench, was effectively an attempt to kind of define a single benchmark suite that kind of understand the pros and cons between some of these different systems that exist today, right? So we tested, again, Apache Hudi, Apache Iceberg, and Databricks Delta Lake as the 3 key formats in that benchmark.
Which one should I use? Which one's the best?
So the answer here is pretty interesting. It depends. It really depends if you're kind of trying to optimize for writes or reads. So for example, Iceberg and Hudi have a very special mode of operation where they support copy on write and merge on read tables. And so that allows them to convert their database from operating in a read optimized setting to a write optimized setting. And so really depending on your workload, you might choose a different tool. And so in general, though, we did find that Delta Lake performed extremely well. And it may not be surprising because it's actually well optimized with Spark specifically to ensure it gets high I/O performance. But I don't believe that's something fundamental to the design of Delta Lake.
Cool. You say they all make different trade-offs there. Did it emerge after you benchmarking them and looking at all the different sort of trade-offs they make that there would be some sort of idealistic system that would pick the correct trade-offs and do best across all the different sort of workloads you evaluated it on? Or is it you always going to have to make some sacrifices somewhere, right? But yeah, is there some sort of potential new system you could develop off the back of that would tick all the boxes and be faster than all the existing solutions?
So I think these different frameworks are adding, specialized like fast paths for specific workloads into their frameworks. We evaluated TPC DS as our benchmark. So it's a pretty general purpose analytics benchmark, but what's unique is we also tested the incremental refresh benchmark. And that's a new representative workload where you continually kind of do small merges periodically with queries interspersed in between. And so in that specific workload, actually a lot of these different systems are adding specialized support for merge on read, which is a new capability that lets you defer the merge or kind of compaction of data until that data is kind of read. And so again, that's what I mentioned, Iceberg and Hudi are implemented, but now Delta Lake, for example, added deletion vectors, which is, I would see as a variant of this kind of system. So the answer to your question in some sense is I think the frameworks are kind of learning from each other and taking kind of the best of each of these different approaches and kind of hybridizing in some way, right? But again, it really depends on the structure of workload. Is it going to be write dominated or read dominated? And what level of transaction support do you need? For example, some systems utilize locking versus others use, optimistic concurrency control like Delta Lake.
I guess kind of I think this is my third to last question now, so it's not the penultimate one, it's the one before the penultimate one. And this is always a really interesting question because I ask this to everybody, and it's really nice to see the divergence in questions and the question is like, how do you go about generating ideas and then selecting projects to work on? Because you're working on some fascinating stuff. Like, how do you decide what to work on? Like, what's your process there for that?
Well, I mean, so like we're both advised by like Jan Stoica, and I think he really indoctrinates us with the idea that you should solve like problems that are real, right? Which is harder than it sounds, because you have to find some sort of very like fundamental problem that actually affects people in industry, and if you can solve it, then would actually provide a lot of benefit to a lot of people. So I think that's definitely something that we look for in terms of selecting research ideas. I think with Skyplane, what was really appealing to you about this project was that it's such a sort of simple part of, or kind of like a basic component of system building, like just like transfer and communication, that if you can make that more performant, then there's so many other things that you can improve the performance of as well. So I think that was really exciting to me, to work on something that was pretty low level and fundamental to a lot of systems. Yeah. I guess, do you have any thoughts there, Paras?
Yeah, my thoughts here are pretty interesting. So when I started working this project, I took some of the best systems I could find for data transfer and other tools like data storage, object storage, all these different technologies. And I just try to see what is the state of the art here, and then how can I kind of hack on these systems? And because all of these systems are open source, right? They're all kind of white box. You can kind of open them up and start to poke around. I began to kind of take a look and see what can I kind of tweak here and there to try to improve the performance. And so, as you started to go through that process, I developed, I think a lot of understanding for kind of the trade-offs in these systems, right? And so that's what I really like about working on real problems in some sense here, is that like there are existing solutions that we kind of can pick up and start to test and kind of take apart, right? And as you kind of go through that process, it's very often there's some very simple insight that's like, just a few feet under the surface of the water that, just needs a little bit of digging to find, right? But that research journey is always very satisfying and sometimes very challenging, but it really takes that kind of, I think, confidence to be able to take kind of an existing solution, kind of rip it apart and say, like, what can we do better here? Yeah.
Oh, that's two really great answers. I can add to my collection now of these answers to this question. That's fascinating. I mean, I guess both you guys come from originally, like you've got a background in industry. I mean, do you find that kind of having that industry experience and then going to do your like do a PhD is a kind of a better path to take in a way? Like you're grounded in kind of, I'm going to go and work on real world problems. I want to solve real world problems. Do you think that kind of helped in a way?
The first 2 years of my PhD were pretty challenging because after spending some time in industry, I was kind of programmed a different way. And I kind of lost that research context, that mindset of which you go through and study these problems. But I think through that journey, that kind of, yes, I think that has grounded my research, and it kind of drives me to try to find problems that I think are actually real in some sense. Like, meaning, if I'm going to work on a problem, I want to always find somebody who will benefit from the solution, right? It may not be today, but at least some point down the line, right? I think what has been challenging about that is, again, like I've had to kind of go back and relearn the scientific method in some sense, like the whole scientific discovery process of how do you formulate an experiment and actually tractably design an experiment to answer that hypothesis. But I think, like, again, they're different mindsets, kind of industrial design versus research. But I think, we now are working on real technology with real impact while still having that scientific contribution. So I think it's a really nice balance to strike here.
Yeah, you're working in the sweet spot. Yeah, for sure. Great stuff. I guess now it's the penultimate question. So what do you think is the biggest challenge now in database, data management research?
That's a really interesting question. What I think after kind of studying this area is that we're kind of in this new world with cloud computing. So we have elasticity, you have scale to zero. So fundamentally, just the pricing model for everything to do with computation has changed, right? And so along with that, we kind of have to revisit a lot of fundamental assumptions and how we build data platforms. I think the ideas themselves that we are leveraging aren't necessarily intrinsically novel, right? So for example, overlay networking is an idea that dates back over 20 years, right? I mean, Jain worked on this back in 2000 in his PhD. And so in some sense, it's a very classic idea. But because the underlying constraints of the system with cloud computing have changed so significantly, I actually think we have to go back and revisit a lot of very fundamental design decisions and how we build and construct data platforms.
Amazing. And I guess now it's the last question. So what's the one thing you want the listener to take away from this episode and from your work on Skyplane?
Yeah. So Skyplane today is open source. We have a blog post discussing how we're able to make transfers across clouds up to 110 times faster and 3.8x times cheaper. You can use Skyplane today both with the CLI tool and also the Python API. So if you're moving data across clouds or just even across regions, we'd love to have people try it out.
Fantastic. And let's end it there. Thank you so much, Sarah and Paras, for coming on. It's been a fascinating conversation. I hope the listeners really enjoyed learning about Skyplane. I know I have. If you're interested in knowing more about all of their awesome work, we'll put links to everything in the show notes. And you can support the podcast by through Buy Me a Coffee, donate through there, and we'll keep making this podcast. And we'll see you all next time for some more awesome computer science research.